This lesson is going to cover the basics of the binary, decimal, and hexadecimal number systems. The lesson will focus more specifically on how these number systems relate to forensic analysis of stored data. For the purpose of this class, more practical applications of using these numbers will be used, as some of these same methods will be used when examining stored media. If you were going for a Cisco certification or some other highly technical exam, you would need to do a lot of time-consuming manual conversions. This presentation and demonstration will use a calculator, as that will be what most examiners will use for on-the-fly conversions during the course of actual analysis. Another topic that we will be covering as it pertains to forensic analysis is the concept of little endian. We'll get to that in a little bit later. Let's begin. The binary number system is the basis for all computer activities. It is machine language, and that is the one that's understood by a computer's hardware. Binary is a base 2 number system. This means that you have two characters which represent mathematical values in this system. All other values are the result of combinations of these two characters, which are a 0 and a 1. In machine language, a 1 represents a certain voltage of electricity. A 0 represents the lack of electricity. Specifically, this equates to on or off. 0 and 1 also represent true or false. All of the other layers which make up the contents of a functioning computer break down to machine language. Decimal is a base 10 number system. It is the system with which we are most familiar. Most of our daily activities involving numbers use the decimal number system. This includes everything from currency to representing statistical values. For example, when we compare quantities in relation to a larger whole, we use the relative value of 100 for percentage. The decimal number system has 10 characters with which to mathematically represent individual values. These are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. All other values are combinations of these character representations. When we are dealing with digital forensics, the finished product of much of what is extracted and converted from a target storage medium will be in decimal format. This is because a good deal of the criminal, financial, corporate, military, and other information that will be used as a result of an analysis will need to be in decimal. Hexadecimal is a base 16 number. What this means is that we have a total of 16 characters which mathematically represent values in this system. These characters are 0 through 9 as in decimal, and also include the alphabetic characters A through F. A represents 10, B represents 11, C represents 12, D represents 13, E represents 14, and F represents 15. All other numerical values will be a combination of these characters. Sometimes these hex values will look just like decimal values. For example, 221 in hex converts to 545 in decimal. Other times, hexadecimal will be a combination of alphanumeric characters, such as 6F2D. In digital forensics, the hexadecimal layer is exactly one layer above machine language. What this means is that when you see, for example, a value of 5D in hex, this two-character combination represents 1 byte, or 8 bits. That's a combination of 8 zeros and 1s strung together. That's a basic synopsis of the binary, decimal, and hexadecimal number systems, and their significance with the practice of digital forensics. In the next section, I'll go over how to convert hexadecimal to decimal. In this demonstration, I'll be using a calculator to convert hexadecimal values into decimal values using a calculator. As I said previously, if this were preparation for an exam such as Cisco's CCNA, you would need to be able to do these calculations manually. For the purpose of this course, it is more practical to demonstrate how these values are actually converted from their native format on a hard disk drive or from flash memory to decimal format, where an examiner can create something of forensic value from it. Before we convert hexadecimal values, we need to cover something known as little endian. Little endian refers to the order in which a sequence of bytes are stored in computer memory. Little endian means that the least significant value of a sequence is read first. In plain English, this means that you will be reading values from right to left. As a general rule of thumb, when you read hexadecimal values from a hard disk for the purpose of converting to decimal, you will use the little endian format. When simply interpreting certain values, such as a signature tag or determining a cluster run, you will read those from left to right. I know it sounds confusing, but it'll all come to you with practice. Having good reference charts also helps. Okay, let's convert the following value into decimal from its native hexadecimal format. 32, 6F, 7D, 4A. When interpreted as little endian, this will be plugged into the calculator as 4A, 7D, 6F, 32. When converting, first make sure that your calculator is in the programmer view so you can convert hexadecimal and decimal values. You can do this through the View option on the toolbar of your Windows calculator. When you convert, make sure that the Hex radio button is checked. Enter the values as little endian as described previously. 4A, 7D, 6F, 32. After you've finished entering the hex values, click the DEC for decimal radio button just beneath the hex button. You will get a value of 124,973,4450. When you are dealing with offsets in a hard disk's memory, you'll need to get comfortable working with very large numbers, as this is how data is stored, addressed, and retrieved. Here's another thing you'll need to note. When looking in a computer's memory, 1 byte of information is represented as 2 characters, like this, 6E. Whenever someone refers to a byte of data from disk memory, in hex, it will be a 2-character representation. That will either be 2 numbers or a combination of a number and one of the letters A through F. Let's do one more conversion. Let's say you're in a block of memory and you come across the following sequence: 44, 7A, DD, CA. After you get your calculator into the programmer view, make sure that the hex is selected as the view and then enter the sequence as the following: CA, DD, 7A, 44. When you've finished entering the sequence, click the radio button next to the DEC for decimal. You should end up with a decimal value of 340,351,2388. That's about it for this lesson. This purpose of the block of instruction has been to lay the initial foundation for physically navigating and analyzing hexadecimal data in memory. One last thing before we end this lesson. When you view a line of physical memory, it will look something like this. It will usually be displayed in a row of 16 bytes unless you change the bytes per row setting. The row is composed of 16 two-character representations which are known as bytes. Each of these two-character representations is composed of 8 zeros and ones. When extracting from a row of hex values such as this for the purpose of converting to decimal, you must enter the values from right to left. This concludes the lesson.